We're going to talk about vector databases. The title of the talk is Making Sense of Vector Databases. Now, before we start, I want to take a brief moment to talk about Google. Google search. And I think it is safe to assume that almost everybody here has used Google search. And if we use Google search, we can search for anything. For example, Taj Mahal. And then we can find interesting articles about Taj Mahal on the internet. We can also use Google image search to look for images of, for example, Taj Mahal. Right? Now, as amazing as these features are, what I find really mind-blowing is a feature from Google called Google Lens. So where you can upload a picture, and then it shows similar pictures or related pictures to the one that we are uploading. So I want to quickly check. Has anybody used Google Lens? Please raise your hand. OK, that's like 80%, 90% of the room. It's almost everyone. It's really good. So actually, we don't know how Google has implemented this. But if we were to implement this, we can actually do this by using vector databases. So that is exactly what we're going to do in this talk. So we will gather sufficient understanding of vector databases so that we can actually build something similar to Google Lens. So let's get started. But first, a very quick intro about me. My name is Balkrishna Rawool. I work for ING Bank. OK, let's start with vectors. First, what is a vector? In mathematics, a vector is a quantity that has magnitude and direction. Now, we all know this because we paid attention in our maths class, right? In computer science, a vector is a group of array or numbers. For example, these. Now, these two things, vector in mathematics and vector in computer science, they are actually both equivalent. They are the two different representations of the same concept. And it is important to understand this equivalency because it would be very helpful in getting the intuition for some of the concepts that we will discuss later in this talk. So let's first see how they are equivalent. For that, let's consider this example where we have a vector with magnitude m and direction, which is represented by this angle theta. Now, the same vector is equal to, we can put this vector on a two-dimensional plane, and we can see that it is same as this vector v with coordinates x and y. In fact, if we extend this analogy, we can also see that a vector which is in three-dimensional, four-dimensional, or even higher dimensional space can be represented by a vector with magnitude and direction. The direction there would be not a single angle theta, but would be a bit more complicated, but we would still have a vector with magnitude and direction. And the elements in a vector are also called as dimensions of the vector. Now, that is because a vector in n-dimensional space can be represented with n different numbers, and therefore those numbers are called dimensions of the vector. OK, now that we have basic understanding of a vector, let's see what are vector embeddings. So typically, a vector is calculated from some data by applying an embedding algorithm or embedding model. And the resulting vector is known as embedding, vector embedding, or simply as vector. So what we have is data or tokens. We let them pass through an embedding model or embedding algorithm, and we get a bunch of vectors. Typically, we put them in a vector database. Now, a good embedding model puts data with similar meaning close to each other in the vector space. And the measurement of this togetherness is called as similarity or distance between two vectors or two embeddings. And we'll discuss more about this in later part of this talk. But now let's look at what is a vector database. Now, a vector database obviously stores vectors. But along with that, it does other operations like inserting, updating, deleting, indexing, and searching like any other database about vectors. Right? And there are a lot of vector databases available in the market. Some of them are listed here, like Postgres, Elasticsearch, Redis, and a lot of them. Postgres is actually not a vector database by default. It is a relational database, but we can add an extension called pgvector, and then it becomes a vector database. Now, in this talk, we are going to use Postgres and VV8 for some of the examples, but we are also going to create a simple vector DB by using Java's vector API. So let's see how we can do that. Let's first see what is Java's vector API. So this vector API actually takes advantage of certain CPU architectures for faster processing. More specifically, it uses single instruction multiple data, or SIMD. SIMD is a processing model where if you have pairs of data and then you want to apply a same operation to all those pairs, you can do all of that in a single CPU cycle. And when we deal with vectors, it becomes a natural choice because vectors are series of numbers, right? And when you want to apply an operation on two vectors, you basically apply the same operation on these pairs of these numbers, right? And therefore, SIMD becomes a natural choice, and that's why it is used in Java's vector API. Right now, it is in its 10th incubation with this JEP 508. Now, what we will do is we will create a simple VectorDB implementation which will store vectors in memory. Also, it will allow us to do insertion, deletion, selection, and searching by using Java's vector API. We'll see that how we can do that. But I also want to do a quick shout out to Llama 3.java, which is an amazing example where Java's vector API is being used. It's a simple implementation to run inference of models, and it is completely built using Java. It's a single Java file, although it has, I think, 3,000 lines of code, but it is still something that's completely written in Java, and it allows us to run these inference models. It's done by Alfonso Peterson from GraalVM team. So this shows, this is actually an amazing example of where you can use Java's vector API. What we are going to use it is to write a simple vector DB. Okay, so let's see how we can do that. I'm going to move to IntelliJ, and I hope the font is big enough to read, or shall I increase? I get a yes. Okay, I get a yes. So I'm just going to continue with this font. So what we have here is, let me squeeze everything up. Let me show you a class, vector. So this is actually implemented. So this is actually a record which has an array of doubles called embedding. So this represents a vector. And we have some methods here, which are basically operations that you can perform on a vector, like add, subtract, dot product, magnitude, normalize. We will see what these things are a bit later. But these methods are implemented using vector API, as we see here. I'm not going to go through the implementation. I will share the link to the source code so you can take a look. The important thing to note here is that we have a representation of a vector. It is a record. And we have some operations that we can do on it, and they are implemented by using Java's vector API. And then we have a class called VectorDB. So this is actually the vector database, and it has a hash map with vectors and their corresponding data. So it stores vectors and the data in a hash map, and that is our simple VectorDB implementation. Now, it allows us to do insertion, selection, deletion, and also there is a method called k-nearest-neighbors. That's an important one. So what this method does is if you pass a vector, it gives you other vectors which are close to this vector according to this distance calculator. So this method gives us k vectors, k number of vectors, for a given vector using a certain distance calculator. Distance calculator is actually an interface which has a simple method distance. So you can pass any distance calculator, and it will calculate vectors which are closer to this vector, k number of vectors which are closest. Also, there is an overloaded method, k-nearest-neighbors, which does the same thing, but it takes a similarity calculator. Similarity calculator has a method called similarity and gives similarity between two vectors. Again, we'll discuss distance and similarity a bit later, but I think the important thing is this method, k-nearest-neighbors, which gives us k number of nearest neighbors for a vector for a given distance calculator or similarity calculator. Okay, so that's how we can implement a vector database by using Java's vector API. It's a pretty simple implementation. And then now let's move on to the first example. So we are going to put to test the things that we just discussed, vectors, vector embedding, and we'll see how that can be implemented, and we'll see if that actually theory checks out. So in this example, the world only consists of gray colors. So there are only gray colors, and all embeddings are one-dimensional. So basically, we have this 10 different colors, ranging from white to black. And then these are mapped to some numbers, 0 to 9, right? And these numbers are converted to one-dimensional arrays. So basically, our embedding algorithm or embedding model here is just a mapping from these colors to these numbers, which are then one-dimensional vectors. So that's what we do. We take all these numbers, map them to these vectors, put them in this VectorDB, which is our simple VectorDB implementation. And then we query. So we randomly pick one of the color, and then we query to find out similar colors, right? So we'll put our theory to test. Now, let me show you how the front end of this application looks like. So here we have all these colors. I think I should make this a bit smaller. Yeah, so we see all these colors, and we can randomly select one of these colors. It will move here as a selected color, and then we'll query similar colors in our vector database. Now let's look at the backend for this example. So this is a Spring Boot application, and it makes use of a REST controller. So here is a REST endpoint called nearest neighbors, which takes in a color and gives you the nearest neighbors for this color, basically similar colors. Right? So how we implement this, we call this method, where we actually have a vector DB instance, and it already stores all these colors with their corresponding vectors, which are nothing but the single-dimensional or one-dimensional vectors, these numbers 0 to 9. And then when we call nearest neighbor, what we do, we convert this color into its vector, basically map it to a number, and then we call k nearest neighbors, which gives us similar colors or vectors closest to that vector using a distance calculator. Now we'll discuss what Euclidean distance is, but we use that here to get nearest neighbors, basically similar colors to our color. And that we return to the front end, and then we show them here. So let's see how it works for an example. Let's say we pick T. So we see this color here, and we see its neighbors. So the first is basically the closest color is itself. So we see that here. And then the colors which are close to it, like E and C, with their vectors and with their distances. We can do it for other colors, and we actually see that similar colors are being shown here. If we do it for white, it shows this and this color. That is quite natural. So basically what we did was our understanding of vectors, vector embedding, we have put that to test with this simple vector DB implementation, and we see that it checks out. So let's move on to the next concept, which is similarity or distance. There will be a bit of math in this section. So let's see what is similarity and distance. So two vectors that have similar meaning, or two, let's say, data that have similar meaning are close together in their vector space. Similarity and distance is a measurement of how close they are. So basically, if they are really close, they are similar. They are far away, then they are not that similar. And there are many ways of calculating the distance or similarity. Some of them are listed here, and we'll go through them one by one, and we'll understand what these measurements are, starting with Manhattan distance. So for these two vectors, v1 and v2, which are in this three-dimensional space, the Manhattan distance between these two vectors is basically sum of their distances along these x, y, and z axis. So that would be this. Then the next one is dot product similarity. So dot product of these two vectors, again v1 and v2 in this three-dimensional space, is nothing but the sum of the products of their x, y, and z coordinates. So it is this, x1 into x2 plus y1 into y2 plus z1 into z2. And then the next thing is Euclidean distance. So Euclidean distance between these two vectors is a straight line distance between these two vectors, which in this case is this, basically square root of sum of the squares of their distances along x, y, and z axis. Now the next thing we'll discuss is cosine similarity, and for that we have to understand magnitude and normalization of a vector. So for this given vector v in three-dimensional space, its magnitude is nothing but its length from its origin. So in this case, it becomes this, square root of sum of the squares of x, y, and z coordinates. And then normalization or normalized form of the vector is nothing but the vector but without its magnitude, which means it is unit vector in the same direction. So basically magnitude is a vector without its direction, and normalized form of vector is vector without its magnitude. So in this case, the unit vector would simply be this vector divided by its magnitude. Okay, so now that we understand magnitude and normalization, let's understand what is cosine similarity. So cosine similarity is simply cosine of the angle between two vectors. So in this case, we have vector v1 and v2 in three-dimensional space, and the angle between them is theta. Therefore, the cosine similarity is cos theta, which is again same as the dot product of these two vectors divided by product of their magnitudes. Okay, there was a bit of math involved in similarity and distance, but we'll put this math to test with the next example where we'll discuss cosine similarity. So for that, what we're going to do is we are going to expand the first example that we discussed, and we are going to basically go from gray world to more colorful world, and the colors will be ranging from RGB 111 to RGB 255, 255, 255, basically a lot of colors. And the embedding algorithm that we will use is that we'll map these colors to a vector with these 3 RGB values. So we get a 3-dimensional vector, and then we will normalize that vector. Now, this is still a good embedding model, like in the previous example, because here also the colors which are similar, they map to their vectors in this vector space close to each other. Right? Similar colors are close, and therefore this is still a good embedding model. So what we do here is we take all these RGB colors, we let them pass through this embedding algorithm, and we get a lot of vectors for these colors. We put them in our simple vector DB implementation, and then we're going to query. So we're going to randomly pick a color and find similar colors. Okay, so let's take a look at the front end for this application. So what we have here is actually a color, which is shown here at the top, and there are some buttons to change the RGB values. So I'm just going to change these values, and the color is getting changed. And then what we see is these RGB values, and we see here a vector with these 3 values, so 3-dimensional vector. And what we store in the database is actually normalized form of this vector. Right? So we actually have database, all these colors with their normalized form stored in the database. And now we are going to click on Show Similar Colors, where it will show similar colors, basically neighbors of this, this vector. So let's take a look at the backend. Again, backend is a Spring Boot application with a controller. It has an endpoint called nearest neighbors. So for these RGB values, it returns nearest neighbors or similar colors. Right? So let's see what is happening here. We again have a vector DB instance, where all these colors are stored along with their vectors. And when we query nearest neighbors, we create a vector of these RGB values, and then we call k nearest neighbors, which basically gives k similar vectors or k neighboring vectors for this vector using cosine similarity, because cosine similarity is what we are testing now. Let's see how the cosine similarity calculator is implemented. As we discussed earlier, cosine similarity is nothing but the dot product of 2 vectors divided by the product of their magnitude. So that is exactly what we do here. And once we do that, we return the similar colors or neighboring vectors for this given vector. And then we show that on the front end. OK, so let's see what happens if I click here. I see a bunch of colors which look similar to the given color. I can actually change these values and then get similar colors for whatever that I'm selecting here. Now, if you look at the results, we see similar colors to the given color. So basically, our theory checks out here. We see the vector, the normalized form here, but also we see cosine similarity. So basically, this is the cosine similarity between these 2 vectors. And the first result that we get is always the color itself, because that is the most similar color to itself, right? For that, the cosine similarity is 1. So the value of cosine similarity ranges from 1 to -1, 1 being the most similar vectors, and -1 being opposite vectors for the definition defined in the embedding model. So that's about cosine similarity. Let's move on to the next part, which is embedding models. So embedding models convert input data into vectors, right? And these vectors, these resulting vectors, they capture the meaning of the data, but they also capture a relationship between this data. And there are many embedding models, like the ones listed here, but there are many more. Now, in this list, models like Word2Vec, Glove, and BERT, they work on text data. So basically, you can pass text inputs, and it converts those texts into vectors. And then we have models like CNN and Image2Vec. They work on image data. So if you pass images, they convert those images into vectors. And then we have GPT, CLIP, and other models which are multimodal. So you can pass text, image, video, audio, or whatever input that they can have, and then convert that into vectors. So what we're going to use for our next example is Word2Vec. So we're going to test Word2Vec in this example. So what we're going to do is we're going to convert words into vectors. And the embedding algorithm that we'll use is Word2Vec. More specifically, it will be deep learning for J Word2Vec implementation applied to 4 Wikipedia pages. And we'll see that the resulting vectors contain meaning, but also relationship between tokens. So what we'll do here is that we'll take 4 Wikipedia pages, And the 4 pages that I have selected from Wikipedia are man, woman, king, and queen. And we'll see why I have selected those 4 pages. So those 4 pages are passed through this word-to-vec embedding algorithm, and that gives us a lot of vectors. We put them in our vector DB. We are still using our simple vector DB implementation. And then we randomly pick a word and find its neighboring words, basically words that are similar in meaning to the given word, or words that have some connection to this given word. Okay, let me show you the front end for this application. Looks like this. So here I'm going to input a word, and by clicking on show vector, we'll see the vector for that word. And by clicking on show similar word, we'll see words that are close to it in the vector space. Right? So that's what we'll see. There is a bit of equation here. We'll take a look at that in a minute. But let me show you the back end. Again, it is pretty similar to earlier examples. So what we have is a controller, which has a bunch of endpoints here. The first one, embedding. It gives embedding basically the vector of the given word. Then the next one is nearest neighbors, which for a vector, for a word, what it does is, it gives the neighboring vectors for the given word. And what it does, it has this vector DB instance. And what we have done is we have taken the 4 Wikipedia pages and converted them into vectors. So what we are doing here is in the initialize DB part, we have this method create and store vectors. So we take this data file, which is basically, as you will see here, copy paste from Wikipedia of these 4 pages, king, queen, man, woman. And what we do is that we apply the word-to-vec embedding algorithm. So in this case, it is a deep learning for J implementation. And that gives us a vector file. This vector file is nothing but words from these Wikipedia pages and their corresponding vectors. So it's a long list of these words. So then what we do is we use this nearest neighbors method. And it basically takes a word, converts that word into a vector, and then find its nearest neighbors. So it gives us few words which are connected to that word in that vector space. Again, here we are using cosine similarity calculator. And then we return those words back to the front end. Okay, let me add a word here called king, and then show its vector. So as you can see in the word-to-vec implementation, we have hundreds of dimensions, so this vector is really big. And when I click on show similar words, we'll see vector words in the vector space which are close to that vector. If I click that, I get these words, king, title, kingdoms, emperors, emperor. Was is also there for some reason. But basically, we see most of these words are connected to king or similar to king in some or the other way. So what we see is that the vector is capturing meanings, or this embedding algorithm is capturing meanings from these words. And now for the equation part. So the embedding algorithm also captures relationship between words. And in order to show that, an example that is typically used is one where you take a vector for king, and then you subtract a vector for man. So this should give us a vector which should represent royal characteristics in some way. Right? You take a vector for king, subtract vector for man. Basically, resulting things are royal characteristics in a vector form. And when you add to that a vector for woman, this should give you a vector for queen, right? Because queen is a woman with royal characteristics. And let's see what happens when I click this equals button. Let's go to the back end and see what is happening. Again, in the controller, I have this method called equation, which takes these 3 words, start, to, subtract, and to add. And what it is doing is converting them into vectors, and then it applies some vector arithmetic. So you subtract the vector and then add the other vector. And for the resulting vector, we find its nearest neighbors. So let's see what we get by doing this equation. We result all these vectors to the front end, and we show words with their cosine similarity. So if I now click equals, what I get is, well, queen is here as the second most close result. Ideally, it should be the top one, but still, I think it is pretty good for a small set of words that we have used with 4 Wikipedia pages. So what this does is it shows that the embedding algorithm not only captures the meaning of this data, but also captures their relationship. So that's about embedding algorithms. Moving on, we have indexing algorithms. So for any database, when you have lots of data, right? You need indexing to efficiently search through that. And that is the case also with vector databases. So there are a bunch of indexing algorithms for vector databases, like KD-tree, R-tree, LSH, ANOI, HNSW, and SCAN. So these indexing algorithms are categorized into 3 categories. Some of them are tree-based, some are graph-based, and some are hash-based. KD-tree, R-tree, and ANOI are tree-based. LSH is hash-based. And HNSW is graph-based. We'll discuss HNSW in a bit more detail on the next slide. A scan is basically a hybrid approach, so multiple techniques combined together. So let's take a look at HNSW, or hierarchical navigable small world, in a bit more detail. The small world part here refers to the saying, it's a small world after all. Basically what that means is, when you have a natural network, the nodes tend to form clusters. For example, if you have a social network with person A, B, and C, and if person A is friends with person B and C, it is very highly likely that B and C are also friends with each other. And because of that, these nodes tend to form clusters. And that principle is utilized in this indexing algorithm. What this does is, it actually, here the vectors are plotted onto a graph, with each vector being a node, and the closed vectors are connected by edges. And then we put them in different layers, with the lowest granularity at the top and highest granularity at the bottom. And what we do for searching is, we start at the topmost layer with a fixed entry point always, and then we navigate through that graph to find the closest node for the query vector on that layer. And then we use that as an entry point to the next layer and repeat the process until we reach to the bottommost layer, where we have the highest granularity vectors, and that's where we find a vector which is closest to the query vector. Okay, we are going to use HNSW in our next example. So here what we are doing is, we're going to index a relatively large wiki data set. So in the last example, we used 4 Wikipedia pages. Here we're going to use 10 Wikipedia pages. And the embedding algorithm that we're going to use is Llama 3, which is applied to 10 Wikipedia pages. And we'll find 5 nearest neighbors. Again, this picture keeps on repeating with different text on it. So here we're going to take our data as 10 Wikipedia pages. And all these 10 pages are about mathematics. So anything related to mathematics, we can search. And then we get their vectors. We put them in Postgres with pgvector. So it's a different database this time. And with the prompt, we are going to enter some text related to mathematics, and we'll find its neighbors. So let's take a look at the front end for this application. It looks like this. So basically, you enter some text about mathematics, and then you search. The back end for it looks like this. So here we have, again, very similar thing, single endpoint query. We search for it. And the first thing that we do is we use Ollama embedding client to get the Ollama embedding or vector for the given query. And then we use that to basically search in our database table, math big vector store, and we find 5 neighboring entries for it. Now let's take a quick look at this table in our Postgres database. Yeah, so this will show us the columns that are present. So this table has this content column, which stores the entry from the Wikipedia page, and then embedding, which is the vector for it. And as you can see here, we are using HNSW indexing and indexing this column embedding. OK, let me query this. And for this demo, I can't show the demo here in this, this way, because I cannot install an LLM on my machine because of our organization's policy. So I'm going to show a video of recording that I made from another machine. So for that, let me move over to here and show you this video. So what we do here is, again, we are doing using HNSW indexing. So we are going to enter a text which is related to mathematics. So we are asking question, what is algebra? And it will go to the vector database, search for those indexed Wikipedia pages, and then get some data related to it. So it's basically giving some text related to algebra. And it actually quite matches with the semantics of the input. So it is showing answers to our questions, for example, differential calculus. It will show things related to differential calculus. Because this is mathematics, we can also ask questions about mathematicians. So we can ask, for example, tell me about Newton, and it will tell things about Newton that it finds in its database. So yeah, so that's how we can basically get these results really fast because we are using HNSW indexing. Now, here in this example, all these inputs are formed as sentences. But they don't necessarily have to be sentences. They could be anything, right? It's just searching for the data in the database. But it would make sense to use these as sentences if you are interacting with an LLM, right? If you are interacting with an LLM, you can also use vector database to augment the context into your prompts. And if you do that, that pattern has a name, and it's called retrieval augmented generation. And that's the next thing that we'll discuss. So what we do in retrieval augmented generation is we augment the prompt to an LLM with specific knowledge that is relevant for your context, right? Like here. So typically when you go to LLM, you send some prompt and you get some response. But what you can do is you can store your context as vector entries in your vector database, and then you can, whatever prompt you're sending, you basically go to the vector database first, get some information related to your context, and augment that with your prompt and to send to an LLM. That gives you context-specific information back. Okay, we are going to look at an example for this, where I'm going to create this fictitious comic book store called Epic Comic Co. And I'm going to use embedding model Llama, and vector database is Postgres with pgvector. And basically put the FAQ for this fictitious comic book store in the vector database. And then when we ask the question to this LLM, we first go to the vector database to fetch some data which is relevant for our question. Okay, again, the UI for this example is pretty simple. We enter some text, and then we interact with this LLM. And at the back end, I will show you that it's, again, not that complicated. So we have only one endpoint called chat. And then we basically, what we do here in this chat is interact with the LLM. But there is a flag for RAG. When the flag is turned off, we just directly go to this Ollama LLM, and then we just show whatever response we get. But when RAG is turned on, what we do is we first get the vector by using Ollama embedding client, and then we use that vector to query our vector database, Epic Vector Store in this case, which actually contains our FAQ for the Epic Comic Co, vectorized and stored in this table. So let me show you this. Again, I can't show you live because of LLM. Let me show you the video for this. First, when RAG is turned off. So this is when RAG is turned off, and then we ask a question, who are you? So if we ask the question, we are asking the question directly to Llama, so it will just say, I'm an LLM called Llama. I'll just forward the video a bit. So this response saying it is Llama. And then I'm going to ask a question which is specific to Epic Comic Co, and it does not have the context, so it cannot answer that question. Normally, it should say, I don't know anything about it, but sometimes it makes things up, and that's called the hallucination of LLM. And I think in this case, when I recorded, it did make something up. So we'll see what that responds with. So it says that, yeah, I know about it, and there is a 14-day return policy, because we're asking questions about return policy. But this is actually not true, as what we will see. Let me show you the real FAQ. And what we see in this FAQ is that the return policy clearly says that it has to be within 15 days of purchase, so not 14. And also, very importantly, the returns are only accepted at the store in person. So our LLM did not give this information because it lacked the context. So now I'm going to show you when the RAG is turned on, what do we see? Again, I'm going to ask the same questions. The first one I'm going to ask, who are you? And it should say it is from Epic Comic Co. Yeah, it says that it is from Epic Comic Co, but it also gives itself a name, Emma. I don't know where the name came from, but the LLM just gave itself a name. And then we're going to ask a return policy for Epic Comic Co. If we do that, in this case, we get the actual result from the FAQ back. It says they are allowed within 15 days and only accepted in person at the store. So this way, we can use RAG to inject context to our prompts. And it can also be useful for adding memory to our LLM. And this brings us to an example where we are going to mimic the Google Lens. So we're going to use image-to-vec embedding here, and we're going to vectorize a lot of images. In this case, I have used touristic places in the world or world wonders. And the embedding algorithm is image-to-vec, and the vector database is VV8. So So we put that into the vector database, and we are going to query a new image, which is not present in the data set. So we'll see how it works. OK, so in this case, I have this example already here. So it's, this is how the front end looks like. Call it frugal search because it is frugal with the UI. And this also shows that I'm a backend engineer because the front end looks like this. And let's look at the backend for this, this example. So here, again, it's pretty simple. One endpoint takes a file. It looks at this wonder image class. So in VB8, you have classes and not tables. And then you have fields, not columns. We are going to query this field image for the given file. And I'm quickly show you how the wonder image database class looks like. So I'm going to query for one image, and this is basically the image is stored as base64 encoded version, and that's what we see here. Let's query this. I'm going to choose a file, and okay, vector.db under test images, and I'm going to select Taj Mahal here because that's how we started the talk. And now if I search, it should find Taj Mahal pictures in the database. It does. Now, you might think I only have Taj Mahal pictures in the database, so I'm just going to choose another thing. This is Colosseum, and we should see pictures of Colosseum in the result. That's what we do. Now, this is quite amazing and interesting to see that this works. But we can actually extend this example, right? We can even have a database of celebrities' pictures, and we can take a selfie and match, and we see which celebrity we look like. Now, it would be a shame to just put the idea out there and not have it implemented. So I have this next example called celebrity lookalike. Now, this is the moment where I look for a brave member from the audience who is interested which celebrity they look like. Is there anyone who is interested?
It's my birthday, so I would like to do it.
Oh, sure. Yes, come on up. Well, first of all, happy birthday.
Okay, thank you.
What's your name?
Robert.
Robert.
Yeah.
A round of applause for Robert. Come on here. What we're going to do is we are going to make a picture of you. So let me open photo booth on this thing. OK, can you come here, please? And I'm going to make your picture. You can smile. Wait. Yeah, now we have your picture captured. You can still stay, because we still need to see which celebrity you look like. Now, let me move this over to my selfies folder. And as you can see, I have tested it many times. I hope we have you here somewhere. This is probably you. Yeah. So I'm going to crop this just to see your face, and because we don't want anything else to match. So let's use only your face, and let me save this. Perfect. Now, Robert, do you accept the GDPR cookies to upload your picture?
I don't have a choice, right?
Oh, yeah, exactly. OK, I think that's you. OK. Now, one warning. So I'm just using image-to-vec embedding algorithm. This is not optimized for faces. So you get pretty wacky results sometimes. But let's see what we get this time. I have no clue what we're going to find out. Let's click search. We get George Clooney. That's not bad, is it? OK, thank you, Robert. Thanks a lot. So that was the last demo I had to show you. If you're interested in the source code, it is present here. And if you have any questions or comments, feedback, you can always reach out to me here. And talking about feedback, if you did like the talk, then you can also consider rating it nicely in the app. Now, before you take your phones out and start rating 5-star to this talk, let me do a quick summary of what we discussed. So we started with what is a vector, right? And then we added these concepts one by one. And then we looked at these examples with increasing complexity, finally to reach an example which was quite mind-blowing. And I hope it was fun. Thank you.